Hey everyone, so lesson 2 of Transformations and Symmetry, chapter 9, is all about symmetry, and that's exactly what you think it is. It's the same symmetry that you have done before in maybe an art class. But we're going to expand upon that idea and talk about more than just line symmetry, but also if something has plane symmetry or rotational symmetry. Okay, and so first thing is just reviewing line symmetry. So remember, a line symmetry is when a figure can be mapped onto itself by a reflection. So some sort of reflectional symmetry, like when you're standing and looking in a mirror, or if you draw a line down the middle of your face. And then a line of symmetry is the line that gives the figure that symmetry. So this is line symmetry is what something has if you can draw that line down the middle. So if it has line symmetry, you can draw a line of symmetry and vice versa. And so the difference between those two is minute but important. Okay, and so some examples here, like everything in an object matters. So when you're looking for line symmetry in the circle, for example, without the smiley face on the inside, there would be an infinite number of places that we could fold a circle to fit on top of itself. So I could just keep drawing lines as long as it goes through the center. It would be line symmetry. But because of the existence of that smiley face, we have to be more specific. The only place we can fold this is right down the middle, so that, you know, this maps onto this side maps onto this side. Everything maps onto each other, so this only has one line of symmetry. Right. And then again, squares are something that we can fold numerous places, but with a rectangle we can fold it, as you guys know from grade school, we can fold it hamburger style or hot dog style, so that this maps down to here, or that this maps over to here. So this one has two lines of symmetry. Letters work the same way. Depending on the font that you use, it might create different symmetries or reflections or anything like that. So let me pull up a couple examples here. And so, like, for an example, this one here has a line going right down the center where we can fold it over, and so it creates a line of symmetry in this specific image between those. But we can look at, again, individual letters as well and see what kind of symmetry they have. So you have vertical symmetry and you have horizontal symmetry. So if I go back up to this rectangle, this is a vertical line. Here's your horizontal line. This question is asking how many of the letters have a horizontal line of symmetry. So I'm just going to follow this line in my grid here. Draw it right down the middle. Okay, and look at which ones will fold over on top of themselves. So the C will, the W obviously won't. Now if this asks for vertical line symmetry, our W has that. It does not have horizontal. Our H does, and the H actually has both. So you can check for that. This one's not asking that. The I has actually both. The M doesn't have any. The Q doesn't have any. The R does not have any, but this K does. And so you see here we have 4 letters that have a horizontal line of symmetry, or they have horizontal symmetry in them. Okay, so moving into plane symmetry. Plane symmetry is when we look at 3D objects. And if they can be cut in half by a plane. So instead of just a line, you have to slice them by a plane. It would be like taking a piece of paper and putting it like down the middle of a pie. So if you've ever like seen those like fancy cheesecakes that they have at the store, where they have the 4 different kinds of cheesecakes, a lot of times there'll be like cardboard in between them. That creates that plane symmetry on either side of those. The plane of symmetry, so again, the difference here between when it has plane symmetry and what creates that, the plane of symmetry is the plane itself that cuts the 3D object in half. So depending on what you're looking at, that could be different different shapes. So when you have a 3D object, you're going to dissect it. So if I'm looking at this prism, all right, I see a triangle, a rectangle on the bottom here, and then a square in the back. So I want to check each of those individually for symmetry. This triangle does not have either, it doesn't have horizontal or vertical symmetry, so this one has no symmetry. A rectangle we talked about earlier has 2 lines of symmetry. And a square, because all sides are equal, has the same 2 lines as a rectangle, but also has these diagonals here. So we can cut it here. So it actually has 4 lines. Okay, sorry, I needed to change my color so you could see something here. All right, so when you put all those together in this 3-dimensional shape, you can see here that we have in this square, and I'll do the best I can to draw these, we have those 4 lines of symmetry. There's a little wonkadoo. Okay, in the rectangles we have the 2 lines. And in this whole figure, and in those triangles we didn't have any, in this whole figure it's not symmetrical like across this line, right? But if you look closely, you'll see, hopefully, that this long edge on your rectangle matches up on both top and bottom with this middle one on the square. Well, when we match those up, we get this shape up here. All right, so this shape has plane symmetry. And this first one up here happens to be the plane of symmetry. All right, because we can insert that one at any point along that line in the middle, right, which matches up with those lines there to make those symmetrical. All right, so it makes both the square symmetrical, it makes those rectangles symmetrical, so now this whole 3-dimensional figure is symmetrical. Okay, when a figure can be mapped onto itself by a rotation of 180 degrees or less about the center of the figure, then it has what's called rotational symmetry. What that means, okay, so here you can see as we turn this image, it's going to click into place, so there it's going to stop again without making a full rotation around. So every time it clicks into its own place, even though it's not making a full rotation, it looks the same as it originally did. So as long as you can do that without it spinning all the way around in a full circle, then it has what's called rotational symmetry. Now all of these are spinning on the center of that line. Okay, so if I put like a little pin right in there, right in the center, it's just spinning around that pin. Okay, so that's what I mean by rotational symmetry. The magnitude of rotation is the same as the degree of rotation. So how many degrees is it turning before it locks back into place? All right. Let's clarify that there. So how many degrees does it spin? So is it a 90-degree rotation? Is it 180? Is it 60? What would that be? The center of symmetry is the center point of rotation. So again, if I were to like stick a pin in the middle of a pinwheel, that is the center of rotation because it's turning about that center. All right, so where can you put your pin down? Point of symmetry is when a figure has rotational symmetry of 180 degrees. So you can only spin twice, like a rectangle would have a point of symmetry. It's turning exactly 180 degrees, click into spot, turn another 180 degrees, click into spot. So that's point symmetry. Okay, so do the figures below have rotational symmetry, or do they have point symmetry? All right, so for this isosceles triangle, can we stick a pin right here and turn this and have it lock into place without making a full circle around? If you said no, you're right. This one has no rotational symmetry. I need to specify that because it actually does have line symmetry. This next one does have rotational symmetry. All right, and if we spin it 180 degrees, it locks into place, so it also has point symmetry. This regular pentagon has rotational symmetry. But if we turn it 180 degrees, it's going to be upside down. So it would look like, let's see if I can draw this successfully upside down. It would look like something like this. Only a little better than that, right? And so that doesn't look identical, so there is no point symmetry. And then this last one, again, yes, it has rotational symmetry. This one looks the same from all sides, so it clicks up, moves up, moves up, moves up. So at 180 degrees, it's going to look exactly the same. So it also has point symmetry. All right, so as we spin these, the degree of rotation is talking about, again, how many degrees can you spin it before it locks into place, before it looks identical to the pre-image. Because there is 360 degrees in a circle, if we just divide that by the number of times that we can spin it, it will give us our degree of rotation. Notice that this is specifying specifically regular polygons. And for something to be a regular polygon, it has both, equilateral and equiangular. All right, so which figure has 120 degrees rotational symmetry? A square, equilateral triangle, hexagon, or pentagon? So this is asking, when we take 360 and divide it by n, which one of these will give us 120? So we multiply by n, and we get 360 is equal to 120n, divide by 120, and n equals 3. Well, that's number of sides. The only thing listed in here with 3 sides is B, an equilateral triangle. Okay, and then last is axis symmetry, and this again has to do with three-dimensional figures. When a 3D object can be rotated around an axis or a line and be mapped onto itself with a rotation, then it has axis symmetry. So it's kind of combining line symmetry with rotational symmetry. So we're sticking a pin or a pole right down the middle of an item. The line that gives a 3D object axis symmetry is called the axis of symmetry. So again, noting the difference here between an object having and then what an object needs to show that. Okay, so it has axis symmetry if you can show that it has an axis of symmetry. It is the actual line. So for example, if we were to stick a pole right down the middle of the cylinder, then we can spin it about this pole and it will constantly look the same. So yes, this has axis symmetry. And that's pretty much it for symmetry. You don't really do that in a graph unless you're talking about reflection. And so have a good night.